There you go. There you go. I can take you to the moon. 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 Depends on what you're trying to do. This ain't really homework, but I gotta do it. Hopefully, I'll be done before 1. Then I can start dynamics. There you go.
Welcome to Introduction to Electrical Systems 1. This is another video on the topic of electronics. And this time what we will do, we will introduce the two transistors that we will briefly discuss in this course, namely the BJTs and the MOSFETs. So the outline of this video is simply we will describe the basic structure and say a couple of things about the operation of the BJT, also known as the bipolar junction transistor. And we will do something similar and discuss the basics of the MOSFETs, or as known as the field effect transistor. MOS stands for metal oxide semiconductor field effect transistor. So let's get started. First, the BJT. Here is, let me grab my laser pointer. On the on the left here, we have the physical layout of the BJT. I hope you notice from the start that a key difference between the transistors and the diodes, in this case we have 3 terminals attached to this device. They're 3 terminal devices. And the way we build the BJT, we put an N layer on top of a P on top of an N, and we contact each one of this, right? And these 3 terminals, these 3 regions have a name. This is known as the collector, this is known as the base, and this is known as the emitter. On the bottom right here, you have the circuit symbol for this BJT transistor. And please note that this is known as an NPN. Let me grab my pen. If you switch these regions, if you didn't have an N on top of P on top of N, but you had a P on top of N on top of P, you would have what we call a PNP transistor. The way we distinguish the NPN from the PNP is the symbols are similar, but let's see if you can. The difference between the 2 symbols is the direction of this arrow. For the NPN, it points towards the emitter, right? For the PNP, it points towards the base. One way to remember this, the arrow always points to the N region, right? So for the NPN, the emitter here is N-type, so the arrow points to the N-type. For the PNP, the base is N-type, so the arrow points to the base. So let me clean this up. So what we've done in this slide, we discussed the physical structure, if you will. We introduced the names for the 3 regions of the NPN. We introduced the symbol, the circuit symbol for the NPN, and we said what the difference is between the NPN and the PNP. Now we're going to describe what we call the different modes of operation of this transistor. And the modes of operation depend on whether the junctions, let me take you back for a minute.
Bruh.
We have 2 junctions here, right? We have the base to emitter junction. There's a PN junction between the base and the emitter. And there is a PN junction between the base and the collector. So there's 2 junctions. So the operation of the BJT depends on how the base to emitter, BE here stands for base to emitter junction. In other words, the junction between the base and the emitter down here, and the base to collector, the junction between the base and the collector, and how these are biased, okay? So the operation of the transistor depends on how the, let me draw the physical structure here.
That's a good table. Let me write that down. Put saturation. Greater than 0. That ain't it.
Collector here and emitter. So the operation again depends on how the base and the base to emitter and the base to collector junctions are biased. Let's also remind everybody that the two key applications for transistors are as switches and in amplifier circuits and amplifiers. There's a lot more applications, but these are the two main applications for transistors. So let's take a look at this table, right? When both junctions, when both the base to emitter and base to collector are reverse biased. For these junctions to be reverse biased, remember the PN junction? That means the emitter here has to be higher than the base, and the collector has to be at a higher bias voltage than the base. If that's the polarity of the two voltages, that means both junctions are reverse biased, and we say the transistor is in the cutoff region of operation, or the transistor is off. And that's one of the two stages, two states when it operates as a switch. It's the off state of a switch. So when you're operating the transistor as a switch, you want to have, and you want to turn it off as a switch again, you want to have both of those junctions reverse biased. Let me clean some things up. And let me go to the bottom conditions. Let's look at what is known as the saturation region. And in this case, both the base to emitter and base to collector are forward biased. For these junctions to be forward biased, that means the base has to be higher than the emitter here, and the base has to be higher than the collector here. And that would put both of them in forward bias mode. In that case, we say that the transistor is in the saturation mode, and that is the on state of the transistor operating as a switch. So if you were to operate the transistor as a switch,
What?
you want to drive it between its off state and between its on state. You want to drive it between cutoff and saturation. So if you go between those two modes, your transistor will be off or on. Now, let me get my eraser. We have one condition left in the middle. And notice that in this third case, the base to emitter is forward bias. Forward bias, that means base is higher than the emitter. And the base to collector is reverse bias, which means the base here is lower than the collector. The collector is at a higher voltage. When the base to emitter is forward and the base to collector is reversed, we call that mode of operation active mode of operation. And this is where we operate the transistor as an amplifier. Okay, this is a very important region when you operate the transistor as an amplifier. And with this, we've described the three modes of operation to correspond to the transistor acting as a switch, the off and on state of a transistor, and the third mode where you want to operate the transistor if you're using it as an amplifier, which we call active mode. And each mode depends on how the base to emitter and the base to collector junctions are biased. Now let's switch our discussion to the MOSFET. And MOSFET stands for metal oxide field effect transistor. So let's see, also a three-terminal device, right? There's terminal 1 here, 2, 3. This is known as the drain, this is known as the gate, and this is known as the source electrodes. So let's see how this one gets its name. MOS again stands for metal oxide semiconductor. So that comes from the structure for how this is built physically, because we have a metal, the metal of the gate, on top of an oxide. This region here is an oxide. On top of a semiconductor. This is your semiconductor below. So metal oxide semiconductor. That's the first three letters. The FET stands for field effect transistor, and field effect because the effect of a field. We're going to introduce an electric field here, and the effect of that field is responsible for the transistor action. How it is built physically, you can look at this slice of semiconductor again, and notice we have an N-type region next to a P-type and next to an N. So it has some similarity to the NPN, right? You have N on P on N. The big difference is that in this case, we lay on top of the semiconductor this oxide layer and then the metal to make the gate electrode. Okay, this oxide was missing in the case of the BJT. But just adding that oxide there creates a whole totally different device, and we will discuss its operation later.
Yeah.
If you wanted to look at what a MOSFET really looks like under a really high magnification, so here is an image magnified 130,000 times. This is from 2003, and this is the length of what we call the channel here, and it's 173 nanometers. They're much smaller nowadays, okay? But this is what this cross-section looks like under a high intensity, high magnification microscope. The circuit symbols for the MOSFET, we have two types of MOSFET. Just like we had an NPN and a PNP, we have what we call an NMOS, N metal oxide semiconductor, NMOS MOSFET, and we have a PMOS MOSFET, and what the difference is between the NMOS and the
Bop, 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 bop. Loki look cool. I take it to the moon. 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 Busy what you trying to do?
PMOS we will describe later. And these symbols, you can see variations of the MOSFET symbols in the literature. For our purposes, every time we use an NMOS or a PMOS, we will identify them as such. But notice that for the NMOS, the arrow is pointing in, pointing towards the gate. For the PMOS, the arrow is pointing away from the gate. And with that, we've come to the end of this very brief introduction for the BJT and the MOSFET. Questions for you. What does BJT stand for, and how many types of BJT transistors can you name? What does MOSFET stand for, and how many types of MOSFET transistors can you name? What are the two most commonly used applications for transistors? And with that, we come to the end of this video. I hope you enjoyed it. Till next time, be well.
18 minutes. Golly, boy.
Welcome to Introduction to Electrical Systems 1. This is another video in the electronics series. In this video, we are going to describe the operation of a MOSFET. Our quick outline, we will discuss how the NMOS and how the PMOS transistors operate, and then we will look at an example of what we call the NMOS inverter. So let's get started. As we go through this video, I want to emphasize a couple of points that we are going to look at these devices strictly as switches. I want you to know that any type of transistor can be also operated as an amplifier for amplifier applications, but our discussions on the MOSFETs are going to focus on them working as on-off switches depending on what the input will be. As a reminder, here is a symbol for an NMOS type of transistor. The arrow points in, and here is the symbol for the PMOS. The arrow points out. I think I mentioned that before. There is all sorts of similar variations to these symbols being used depending on the textbook or publication you're using. Remember N and P. N stands for N-type, P stands for P-type semiconductor. We use N-type to indicate that the negative charge is dominated in that type of material, and the negative charges are electrons. P-type to indicate positive charges dominate in that semiconductor, and the positive charges are holes. So let's take a look at the operation of the NMOS and PMOS transistors. Recall that the gate electrode is our control. Okay, the gate is going to determine what happens between the drain and the source. So the gate electrode is our control, and we will try, depending on what the gate input is, determine what happens between the drain and the source. On the left hand side, we have.
Wait a minute.
Control, and we will try, depending on what the gate input is, determine what happens between the drain and the source. On the left hand side, we have an NMOS. On the right hand side, we have a PMOS transistor. I will make some changes. By the way, there are some errors in these switches. If you notice, all the switches are closed. That's not possible. Under some conditions, some of these switches will be open. So we will correct some of these errors here. But I want to make another change here for consistency. If you notice, on the left hand side, the two conditions for the NMOS that we are going to examine is for the gate voltage to be greater than 0 and for the gate voltage to be equal to 0. On the PMOS, the gate voltage is greater than 0 here, and here is less than 0. So for consistency, just for consistency in my discussion, I'm going to also make this one here less than 0, okay? So let me get started trying to explain what happens here. First, let's look at the case on the NMOS side. This is an NMOS transistor, and I will explain how it gets its name, NMOS versus PMOS. We put a positive voltage on the gate. When you put a positive voltage on the gate, what that means is that you're going to introduce, remember this is a piece of metal here, you're going to introduce positive charges on the gate. These positive charges will attract negative charges right below the oxide, right? This is an oxide. You apply positive voltage. That means you're putting a lot of positive charge on this metal here, which will attract negative charge on the opposite side. Notice that this gray region of your semiconductor is p-type, right? So if you apply a high enough positive voltage here, and you attract a large enough number of electrons here, the region right below the oxide will have so many electrons that they will overcome the initial number of holes that make this p-type, so they will change this region to n-type. So you will have a region here that's n-type and another region that's here n-type. By applying a voltage on the gate, a positive voltage in this case, we form an n-type region, which we call a channel under the oxide. So now we are connecting, right, this n-type region with this n-type and another n-type between. So we form a channel between the two. So if somebody came to apply a voltage between the drain and the source, going from n to n to n, this looks just like a tiny little resistor. So you will get current to flow between the drain and the source. So by applying a positive voltage on the gate, we created a channel, an n-type channel between two n-type regions, and we created a bridge, if you will, to connect the drain and the source. So electrically speaking, you can think of this scenario down here, right? Between the drain and the source, we have the equivalent of 2 over a resistor, if you will, here, which is that region there. And therefore, you can have current flow. Mechanically, if you were thinking of a mechanical model, if you had a switch, the switch is closed, right? Because you're allowing current to flow. Now let's go and look at this case right next to it, which we still have an NMOS transistor, okay? and we're going to apply a negative voltage. Remember, I'm doing this so that I can be consistent between the two examples. If I apply a negative voltage on this gate here, that means I will pull in a lot of negative charges on this metal. This negative charge on the metal will induce, we will pull in, will attract a lot of positive charges right below this oxide. So the region here below this oxide will have a lot of positive charges. Notice that this gray area, the dark gray area, it's already p-type, right? So by putting a lot more positive charge there, you're not changing the conductivity. It remains p-type. So if you look at what happens between the drain and the source, right? You have a p-n junction here, and you have a p-n junction here, and these are back to back. And again, to be consistent in my drawings, I'm going to make
Diodes,
some changes here. The way
cuz.
the p-n junctions are oriented, the diode should actually be pointing p-n that way, and anode and cathode that way. It doesn't change the end result because these diodes here are
Oh,
facing
you're right,
back
you're
to
right,
back.
you're right. Yeah, yeah,
So
yeah,
if you
yeah.
apply a voltage between the drain and the source, okay, one of these diodes will always be reverse biased. One of these diodes will always be off. Therefore, mechanically now, if you wanted to use a mechanical model, this switch will be open.
Oh my god. This dude's smart. NMOS and PMOS. I should draw that. NMOS. Take it to the moon. Bro, where is it? There you go. There you go. Through the gate. For inputting positive charges which attract the creating a pathway between the what is the thing? What is the D called? Source and what? What the freak? Source. Resistor. Oh, it's a drain. Me ask ChatGPT if I'm on the right track. You explain quickly how NMOS transistor acts. Yup. What the freak? I don't want this explanation. I have a foot channel. Substrate. Yeah. Towards the gym is not conducted because of P type. Yep. When a positive voltage is applied to the gate, an electric field pulls. Oh, go ahead. Where am I? Was it attracting negative charge carriers? Oh, I basically put that. Basically. Now I put less than 0. In the junctions between the N type junctions. The E type semiconductor.
So we've looked at what happens.
Where's drain? Oh, Boy, what the freak? Boom shakalaka. Cool, cool, cool. And this is probably just the opposite, low key.
Happens when you apply positive voltage to the gate of an NMOS transistor. We turn the transistor on. It's this condition here. Positive voltage is our high, and the transistor turns on. When we apply a negative voltage, when we apply a low on the gate, our transistor is off. So I hope this discussion will help us move a little faster through the PMOS. Here is a PMOS transistor. Source and the drain are p-type. The gray, dark grays stand between the two p regions, right? So what we're going to do first, we're going to apply a positive voltage on the gate. Again, positive voltage brings positive charge on the metal. The positive charge attracts negative charge in the region below the oxide. This region is already n-type. So you're essentially making it more n-type. You're not changing its characteristics. So you're still going to have a pn right here and a pn junction on the other side. Let me grab my pen. So if you look at what happens between the drain and the source, the diodes here are correct, right? We have a PN junction over here, and we have a PN junction over here.
Dang it! Speak slower. Oh my bad. I got him in 1.5. The PMOS is the opposite where the P junction is at the source and drain. Semiconductor is N type. So this between attracts positive charges from semiconductor strings. Patch. I put patch. Between P type junctions. What does it say? E? Or am I bugging?
Again, the two diodes.
Oh, that's allergy. Allergy. VG greater than 0. SD. Oh, this one's off. My bad, my bad. Bro, plot. Oh, I'm choking. Boom. TikTok.
Diodes, sorry, let me get my pointer. The two diodes are back to back. So if you apply a voltage between the drain and the source, one of these two will
It's
always
gonna be
be off,
off.
regardless of the polarity of your voltage. So
Yo.
if one of those is always off, that means if you want to think, that means if you want to think of the mechanical model for this, that my switch here will be open. There will be no current flowing, therefore the switch is open. So when you apply a positive voltage, my high on a PMOS, my switch, the gate and the drain, sorry, the drain and the source remain disconnected or off. No current will flow. Let me go to the last case. In this case, we're applying a negative voltage on the gate that will pull in negative charge on the metal electrode. The negative charge on the metal electrode will be imaged, right? Equal and opposite charge on the other side. So if you apply a high enough negative voltage here and you bring a lot of negative charge on the gate, you can bring in a lot of positive charge right below the oxide, so much that the original um, anti-electrons, right, the electrons that were here, they are now displaced by holes by positive charge. And now we are connecting the P region here and the P region there with another P region in between. So the presence, if you will, of that PN transition, that PN junction, is no longer there. So we no longer have PN junctions, but the middle region looks like a resistor, just like this. So if you were now to apply a voltage between the drain and the source, you get current to flow from the drain and the source, and therefore your switch here is correct, is closed. And we've looked
Yo.
at the last case in our tables here, where we applied a negative voltage on the gate of a PMOS low, and we found out that the PMOS turned on. Now, how do these guys get their names then? NMOS and PMOS, right? In this
Because
case,
they
the body of my semiconductor is P-type, right, for the NMOS. And the body here is also P-type, right? These are my NMOS transistor. So the name NMOS comes from the type of channel. Remember, we call this region here when we form a channel that connects the drain and the source. So the name comes from the type of channel you have to form to connect the drain and the source, and therefore turn the transistor on. So if you want to look for the name of the transistor, look at what type the drain and the sources are. And that means if the drain and the source are N-type, that means you have to connect them with an N-type region if you were to have a transistor to be on. In the case for the PMOS, right, we need to form a P-type channel to turn the transistor on, as it is on the right here. And we've shown that earlier during our discussion. So I hope everybody understands the general concept, the general mechanism that makes the NMOS and the PMOS transistors turn on. We apply a positive voltage on the NMOS, like here. We create a negative channel, so we connect the drain and the source that are also N-type, we turn it on. If you understand one of these conditions, you can describe all the rest. So let's take a quick look before we finish here of what we call the NMOS inverter. Remember, when the arrow points in, we have an N-type transistor. We're going to tie it to
when the arrow points in, he said anti. NMOS inverter.
a voltage source. Remember, these are active devices. We need to power them up. So we're powering this up by tying it to a 5-volt voltage source. And we're going to try to see what happens when this input here is high, 1 in digital talk, or low, 0, right? So what happens if this is 1 or 0? So we're going to assume our 1 is positive voltage, our 0 is negative voltage, right? Remember, when we put a positive, let me get my pen. When we put a positive voltage on the gate, we're going to put positive charge.
What is going on? Positive on N type is yeah. That
On the
mean
metal
it
on the
good.
gate, which means inside the transistor, we're going to be putting negative charge. Remember, this is NMOS. That means my source and drain, right? This is my source and this is my drain. My source and drain are N-type. So if I form another N-type region here, I will connect the two and I will turn the transistor on. So what happens when I turn the transistor on? Remember, mechanically, we'll close the switch. And therefore now, by closing that switch, my output is directly connected to the ground. So my output will be 0 when my input is positive. So when my input is positive or high, my output is low or 0. So what happens if we do the opposite? Let me clean this up. Now we're going to take a look at this same NMOS transistor under the condition that we put on a low voltage or a negative Vin, right? Less than 0. If we put a negative Vin on the gate, that means we're going to put negative charges on the metal here, which means we're going to put positive charges in here. If you put, let me get my eraser and clean this up. If I put positive charges right here, my p-type region that was there originally is not going to change. So between the source, as I go from the source, I go to N-type, I'm going to have the p-n junction this way, and from p I go to n and I arrive to the drain, right? As we discussed earlier. So these are back to back. One of them will always be off. Therefore, my transistor will be off. My switch will be open as shown here, and my output will now be connected through this resistor to VDD. Since there is no current flowing, this is open, there won't be any current flowing, so there is no drop across the resistor. The output will
Yeah.
be equal to VDD. So my output, and this is, remember, it's 5. Usually my high is 5 volts. So my output will be equal to that. Positive 5 will be high, and therefore my output will be 1. So as you could have guessed from the name, the NMOS inverter, if you take an NMOS device, it can act as an inverter. If you put a high, it gives you an output of a low. If you put in a low, it gives you an output of high. And with that, we've come to the end of this video. So let's give you a couple of questions. What are the names of the 3 MOSFET terminals? Where is what we call the channel in the MOSFET located? And welcome to Introduction to Electrical Systems 1. This is another video in the series under the topic of electronics. In this video, we're going to discuss the CMOS inverter and then give an example of a
Yo,
logic
where did
controller that
CMOS
will
come
operate.
from? Yo, CMOS battery, boy. There's CMOS battery in my computer. Oh, I forgot to take these. I'm starting to get hungry. Uh-uh. How much? Two, three more.
It's when it's built using CMOS transistors. The outline of the video. First, we will discuss the CMOS inverter, examine its structure and its operation. The C in CMOS stands for complementary, and you will see why. And then we will do an example using MOS transistors of a gate. So let's get started. First, the CMOS inverter. The CMOS inverter is shown right here. And notice that in this case, we have two transistors. We have an NMOS on the left, and we have a PMOS. Here is the PMOS.
Yo, it has
Here
two.
is the NMOS. And the two are working in tandem. They're working complementary to each other. Notice that the gates of the two transistors are tied together. So we're applying the voltage to the gate simultaneously here. The output is taken at the drain of one and the source of the other.
Will it
And
always be
we
on?
power the transistors through one of the drains and we ground the other source. So these are, you can think of them as being connected somewhat in series, but again, the input, the control input to them, the gate, the gates are tied together. So this describes the physical structure of what we call a CMOS inverter. Again, C stands for complementary. All right, so let's examine how the CMOS operates. So on the left, you see the CMOS. I turn it on its side so that it can kind of look, the orientation of it looks the same as the two transistors here. That notice this is a CMOS arrangement, right? We have a PMOS transistor connected to NMOS. Their gates are tied together, and we are repeating here. The difference is that in this case, we're going to apply a high, and in this case, we're going to apply a low. So let's see what happens. So when the input is high, remember high plus on the gate will introduce positive charges here, which means we put negative charges here. That means we're going to create an anti-channel. We're going to connect the two.
NMOS will
My
be
NMOS will be
on.
on, right? So my NMOS switch, remember the
Yeah,
switch
yeah,
here,
yeah.
will be on.
But
Now,
the
based on
PMOS
the
will be
argument we
off.
just made, if you put negative charges here, right, when this is high, this region in the middle remains N-type. So you go from P to N to P. We still have two back-to-back diodes, so the PMOS is off. So this switch here will be open, will be off. And therefore, let's take a look at the output now, which is connected here. By turning the NMOS on and the PMOS off, I connected the output
To the
to
ground.
ground. Therefore, my output will be equal to 0. So the input, remember, it was high. My output is low. This says that this device here it works like an inverter. We put it high and the output was low. Let's examine what happens the other way around when the input is low, right? Again, when you're putting input low, think of it as negative so you can have a better understanding of what happens with the charge. When this is negative, that means I'm putting a negative.
Bro, I wish I could draw that. That's an easy draw.
All right, so let's examine how the CMOS operates. So on the left, you see the CMOS. I turn it on its side so that it can kind of look the
Oh, I got to
orientation of it
draw
looks the
all
same
that.
as the two transistors here. That notice this is a CMOS arrangement, right? We have a PMOS transistor connected to NMOS. Their gates are tied together, and we are repeating here. The difference is that in this case we're going to apply a high, and in this case we're going to apply a low. So let's see what happens. So when the input is high, remember high plus on the gate will introduce positive charges here, which means we put negative charges here. That means we're going to create an n-type channel. We're going to connect the two. My NMOS will be on, right? So my NMOS switch, remember the switch here, will be on. Now, based on the argument we just made, if you put negative charges here, right, when this is high, this region in the middle remains n-type. So you go from P to N to P. We still have two back-to-back diodes, so the PMOS is off. So this switch here will be open, will be off. And therefore, let's take a look at the output now, which is connected here. By turning the NMOS on and the PMOS off, I connected the output to the ground. Therefore, my output will be equal to 0. So the input, remember, it was high. My output is low. This says that this device here it works like an inverter. We put it high and the output was low. Let's examine what happens the other way around when the input is low, right? Again, when you're putting input low, think of it as negative so you can have a better understanding of what happens with the charge. When this is negative, that means I'm putting a negative charge on both gates, right? If I put a negative charge on the gate on the NMOS, it's going to induce positive charge inside, the opposite. So this will remain p-type. So the N regions will remain disconnected. So my NMOS will be off, and here it is, it says off. So my NMOS is off. I'm going to open this switch. So this is off. And if I put negative charge on the top here, we'll introduce positive charge in the channel. It will connect the two P regions, so this will be on. The switch there will close. And notice what happened to my output now. My output now is connected to VDD, which is 5 volts. Therefore, the output is 5 volts. The input low, the output high, right? This is what we call the CMOS inverter. When the input is high, the output is low. And when the input is low, the output is high. This is what we demonstrated.
Ba, ba da, ba, ba da, ba. Wait a minute. Get it how you live it. Yeah, I'll just put the high though. Mm-hmm.
Now let's take a look at what we call here a CMOS gate. Notice we have a bunch of more transistors now. We have
What the
2, 3,
junk?
4 down here, Q1 and Q2. These are PMOS, and these two are NMOS. The arrows here are pointing in NMOS. The arrows here are pointing out of the gate, PMOS. And I hope you recognize this device here, Q5 and Q6. This is PMOS. This is NMOS.
CMOS.
Their gates are tied together. So this is my CMOS inverter. Okay. So in this case, what we're gonna try to analyze the circuit, but all we are interested is really what happens at this node here in the middle. Because once we know what happens at that node in the middle, whatever happens here, the output will be inverter, because again, this is my CMOS inverter, right?
Yes,
All
sir.
right,
Yes,
so what are
sir.
we going to do? We're going to look at all the possible combinations for the two inputs, right? We have two inputs here, an input A and an input B. Input A is fed into Q3 and Q1, and input B is fed into Q4 and all the way into Q2. Two inputs, we have 4 possible combinations, as you see here. If you think of them in terms of low and high, if you think of them in terms of voltage, 0 and 5 volts, if you think of them in terms of our binary system, right? Zeros and ones.
What
So what
the?
happens when both A and B are 0? So this is 0 and this is 0. When you think again about the low input, think about negative voltage, which means it's going to create a positive charge in the channel. Positive charge in the channel of an NMOS is going to keep it off.
Yeah,
So the
off.
two NMOS transistors will remain off. So this switch here will be open, and this switch here will be open. Remember, the operation of the NMOS and the PMOS is opposite, right? So if the low A and the low B at Q3 and Q4 kept them open, if I feed the low at Q1, which is a PMOS, it will turn it on.
Yeah,
So
yeah, yeah.
this switch here will turn on. And if I feed a low all the way around to Q2, it will also turn it on. Okay, so this switch will close also. So notice what happens now, right? This point that we were interested in now got connected to
That's
VDD.
high.
Remember, VDD is 5. So it's high. If this is high, as we put it through the CMOS inverter, the output would be, of course, low. So this is 0. Okay, so let's move on to the next case. Let me clear everything up. Let me make sure I write back in the 0 for the first case.
I understand it now.
Now we're going to do A0, B1. Again, when the input is 0 or low to an NMOS, it will be off, right? So this will be off, which means when the input is high to an NMOS, this will be on. So this will turn on. Now the 0 made my NMOS off. It will make my PMOS on. So this will be on. The 1 make my NMOS on, which means the 1 will make my PMOS here off. So this switch here will be open. But the point of interest again, which is the wire in the middle, the node in the middle, is still connected via Q1 to VDD. So this is still high, which means my output is low. Therefore, the result here is low. Let's clear this up. Let's put the 2 zeros here. Now we go to case 3, 1 and 0. We're going to make this 1 and we're going to make this 0. The 0 here, 0 means negative, charging the channel positive. This will be off because we need an N channel to turn it on. The 0 turns this NMOS off. That means the 1 will turn this NMOS here on. This transistor will turn on. The 1 turn the NMOS on. It will turn the PMOS off. So this transistor will be off. We open the switch here. The 0 turn this NMOS down at the bottom here off, which means it's going to turn on the Q2 on. So Q2 will, the switch here will close. And the point of interest again in the middle, notice that again this node here is connected via Q2 to VDD again. So this is high, therefore the output is low, another 0. We have one case left. Let me mark in all my zeros. Now we have 1 and 1. So the input is 1 here, 1 here. They're both high.
Now it'll be 0.
NMOS transistors on.
I mean 1.
It'll be on. The switch will close. This will be on. The switch
I think it'll be VDD.
And since the NMOS are turned on by a high here, the PMOS here will turn off. So my switch here is open. And the high is going to get fed through all the way around to Q2. That will also be open that switch. So take a look now at the middle point. It's no longer connected to VDD, right? Because both switches Q2 and Q1 are open. So this is not directly connected to VDD, but Q3 and Q4 turned on and now it's connected to ground. So this is low, which makes this high or 1. And this is nothing but the, I'm sure everybody knows that, what we call the AND gate. When all the inputs are 1, the output is also on. If any of the inputs are low, just in these cases, the output is
what the freak?
So this is how you build an AND gate using CMOS transistors. Here it is.
What in a goat?
Some questions for you now. What does the acronym CMOS stand for? In what type of circuits do we encounter CMOS inverters and logic gate blocks? And the last question is describe how the AND gate works. And with that, we come to the end of this video. I hope you enjoyed it. Till next time, be well. Welcome to Introduction to Electrical Systems 1. We have another video here under the general area of electronics. Our topic in this video is operational amplifiers, or as we often refer to them, op-amps for short. And we are going to have a brief introduction in this video. Our outline. We're going to take a look at the symbol for the operational amplifier and provide some terminology, what the terminals are called. And then we will discuss what we mean by ideal op-amp, what the characteristics of the ideal op-amp are. So let's get started. The operational amplifier, again, we refer to them as op-amps for short. Here it is. This is the symbol for the op-amp, this triangle here. And in this case, we labeled 5 terminals, right? The 2 inputs here, these are the inputs. The one corresponding to the negative sign here is known as the inverting input. The one corresponding to the positive sign is called the non-inverting input. This output here at the nose of the triangle, at the point of the triangle, is the output. And these other 2 terminals here are for power supplies. Remember, when we talked about active devices, the difference between active versus passive, we mentioned that active devices must be plugged in, they must be powered up. So these two terminals here provide the external power so the operational amplifier can function. And as we will see soon, the op-amp is actually not a discrete device, okay, but it's made up of a lot of transistors, again, that we know as being active devices. In terms of what it looks like in reality, actually, it comes into, it's an IC, it's an integrated circuit. It comes in a typical package you can see here. This is a plastic housing. Inside you have the integrated circuit, and these are the leads that are connected to the op-amp. In terms of the connections corresponding to the terminals we discussed here, you can see that 2 and 3 are the inverting and non-inverting terminals. 6 is the output, 4 and 7 are, as you can see, minus 15 volts, 7 is plus 15 volts. Now, this is for one specific kind of op-amp. The 741 is the most commonly used and probably the most widely used operational amplifier. And it doesn't only come in this package, it also comes in other packages that contain 2 or more operational amplifiers in them. So again, it's not a discrete device, just like a resistor. You have one resistor, one capacitor, or one transistor, or a diode. The operational amplifier, it's an integrated circuit. It's made up of a lot of devices. We describe the input terminals as inverting and non-inverting, the output terminal and the 2 supply terminals. And as we said, it's quite inexpensive. And the reason we pay special attention to the op-amp is because it's a very simple and very useful device for instrumentation applications.
Oh,
For our purpose,
not discrete device. What does IC mean? Two input terminal, inverting and non-inverting.
for this course, we will only consider ideal op-amps. So those of you that have an interest in the topic, you can actually take an entire course in operational amplifiers. They are, as I said, they're extremely useful in instrumentation applications, and therefore there's been a lot of work done with op-amps. Now let's take a quick look what's inside what I call a simple op-amp. This is the schematic for the 741. Again, the 741 is not necessarily the best, but it's quite cheap and very useful. And notice that you got a bunch of transistors interconnected. There's a capacitor somewhere in the middle. There's also a lot of resistors. I think if you look for the highest number on the transistors, the highest number is 24. So there's at least 24 transistors that make up this operational amplifier. You can see the output terminal is taken here between these 2 resistors and these 2 transistors. That's where the output is taken, right? Here is, remember, the power supply terminals, minus V. It usually gets plugged into a positive and a negative supply. So this goes to the negative supply. You can see here the positive supply. And here is the inverting, the inverting terminal here. It goes to this Q2 actually, and the non-inverting terminal goes to Q1. There's a couple more terminals here. The offset null. It's the op-amps, usually real op-amps have what is called an offset voltage, and you can use these 2 terminals here to insert a resistor so that you can eliminate the offset voltage. This is beyond our scope this semester, so don't worry about this. But the point of this slide again is the fact that what's inside the op-amp is this complicated structure, yet we're going to simplify it and discuss the ideal op-amp, and you will see how simple the analysis of op-amp circuits becomes. Now let's go back to our little triangular symbol here, and I've added a little more information over here, right? So at the input of the op-amp inside, I'm showing R in. So this is the input resistance. If you were to sort of model what the input of the op-amp looks like, electrically speaking, you can model it as this resistance R in here. If you were to model the output of the op-amp, you can model it with this voltage supply here in series with this R out or this output resistance. Notice this should remind you of the Thevenin equivalent, right? So if you look at the output terminals of the op-amp and calculate the Thevenin equivalent, this is what it looks like. So with that now, with the addition of this input resistance, this output resistance, and this voltage control voltage, so we're going to discuss the properties of what we call the ideal op-amp. Before we move on, notice that we have this voltage source here is its output is equal to A subscript OL. OL stands for open loop, and A is a voltage gain, times V plus, which is a voltage V plus that appears here, minus V minus, which is a voltage that appears here. So basically, the op-amp is what we call a differential amplifier. In other words, it amplifies the voltage difference that appears at its terminals. It is going to take V plus minus V minus that appears here, multiplied by this gain, and that output will appear here, and ultimately across the output resistance. So again, if you hear people refer to the op-amp as a differential amplifier, because that's exactly what it is. It amplifies the difference, the voltage difference at its input terminals. But it does a lot more. But first, let's take a look at the, what do I call, the 5 ideal op-amp characteristics. For our purposes, our ideal op-amp, we are going to assume that it has an infinite open loop voltage gain. I briefly referred to this AOL. That number there, we're going to assume that it's infinite. I know you're probably wondering what are we going to do with a number that's equal to infinity, but hopefully I will explain later. We're also going to assume that the op-amp has an infinite input resistance, right? In other words, this resistance here is infinite. I hope that makes a little more sense. Again, AOL will explain later, but if Rin is infinite, what should the input of the input current, that In flowing into the input terminal, if this Rin is infinite, what should In be? Think about that for a minute. We are going to assume for our ideal op-amp that this R out is 0. So this doesn't exist, right? This is a short if it's 0 volts, which you can see that we are simplifying things here. We're going to assume that the op-amp has an infinite bandwidth. Bandwidth is, just briefly, if you haven't heard the term before, bandwidth is the useful range of frequencies that the operational amplifier operates within. And by saying that it has an infinite bandwidth, we're saying it can work for any frequency. Real op-amps have a finite bandwidth. There is a maximum frequency up to which they can operate. Beyond that frequency, their operation degrades. They cannot operate. But our ideal op-amp, we're going to assume it has an infinite bandwidth. Any frequency signal you put at the input, it will accept it and it will process it, okay? And last but not least, that the ideal op-amp has 0 input offset voltage. If you recall in the previous slide, I showed those 2 terminals that I said we won't be concerned with this semester, that they were there so we can adjust the offset voltage of the op-amp. In our case, we're going to assume the offset is 0. Now I want to go back to, before I leave this slide, remember
Infinite input. Pedance. What I mean? Boy, if you don't. Oh. Oh my God, what am I doing?
I asked you a question. If Rin is infinity, if this Rin is infinity, what does that tell us about In? If you answer that the input current is 0, that is correct.
That's what I was
We'll get
thinking.
to that soon. And with that, this is our introduction to our ideal op-amp.
Hey, last video.
Questions for you. Is the op-amp a discrete device? Can you name the 5 important terminals of an operational amplifier? And last, what are the 3 important characteristics of the ideal op-amp? Now I narrowed this to 3. I give you 5. I will let you decide as we go through what the key characteristics are for our course this semester. They're all important, but I want you to focus on 3. And with that, we've come to the end of this video. I hope you enjoyed.
Yo. And there's really one more. But like low key, I'm hungry. Bro, what? How? That's a dispute. How did I sell? 93. What? It's dropped though. Dang it. Bro, I got less than the mean. I forgot what it was on. What's announcement? Wait, isn't Dynamics B a 88? Let me check. Bro, an A is 88. I'll straight, I'll straight, I'll straight, I'll straight, I'll straight. Alright, I'm gonna eat that though. Very good. Oh, I'm upside down. Go. Don't look good. Wait, Oh, you watching Mr. Beast? I know Nugget.
To Jurassic Park.
Bro, that look good.
What the fuck are you doing? Is this a fountain of ranch dressing? Are those chicken fingers? Yeah. That's fucking good. Peace.
How does that even fit?
Thanks. How'd you get in my house? This is from Italy. It's not your average bacon, bitch. Have you ever made pasta before? Yes. You want some? This is nuts. Oh! Embarrassing. Nice. Some butter, bitch. Amazing.
Oh, that looks good.
Buon appetito, bitch.
But something's happening. Bro made Chick-fil-A sauce.
I need the max win.
Time one. That's all it takes. Boy. Yo, you gonna bread the steak? Why you doing that? Oh, why that bread just look majestic? Why you keep doing that? Shout out to oh wait, there you go. Put the boy out here. There you go. Oh, five. Mm. Oh. Yeah. Dangerous move, dangerous move, dangerous move. Still rain. Yeah, it's raining in Tampa, Florida right now. We got 60-degree chance of rain, 20% chance of wind, and 2 degrees Celsius of frost. Still good though. Still shy. Wait, what's it? There are different settings in it. They like, oh, okay, this one more normal. Yeah, I know a little better. Boy, I ain't even strong. No. Hit the John.
span of a month of eating bullshit. Like, I drank a lot of alcohol. I ain't gonna lie to you. I had a thing called rage drinking. Well,
Does anyone know which uniquely qualified staffer Elon and the Doge boys fired from Yosemite National Park?
I do know the answer to this.
It's not Smokey the Bear. Because that's what I thought it was. I thought it was Smokey at first. I'm like, not my dog.
It can only be Smokey, Yogi, or Pookie. I think it was Smokey.
LeBron James. Happy birthday. Jambalaya.
No pagues el próximo mes de tu seguro de auto hasta que veas esto. Tu aseguradora no quiere que sepas esto.
Welcome back. Today, we are going to be revealing the song entries for song competition number 2. Last month's song competition, we had 9 people submit vocals and lyrics to release a song with myself and other artists. This month's song competition, we had 21 people. So, for this video, we're going to be highlighting some of the parts of each song, and then it's up to you to go listen to the full songs and vote on your favorite. To vote for your favorite, all you have to do is go to this playlist right here and listen to your favorite tracks. Each view counts as a vote, and every like and comment counts as 20 more votes. And of course, the song with the most votes by February 28th will win the competition, and we will release the song. So no more time wasted, let's jump right into this. For our first song, we have Al Tiro. Let's check it out.
Primeramente quiero decirle gracias a Dios. El camino no era fácil, pero él sí me cuidó. Saca la bolsita.
I like that. Dude, I love ad-libs.
This ain't the move.
Estoy al tiro pa' cualquier cosa.
Atrocious. Dude, oh, the timing was a little off there, but I really liked it. When it comes that. Okay, I like the creativity. That's what I'm talking about. Come on, now get into it. All right, my take on this real quick. Eddie, I'm gonna actually go listen to some of your music. Your voice, it just like, it seems interesting with this, but either way, it sounds invented it. All right. Similar flow.
This ain't the move. See, what they need to get on is
Bad bitch, get on, yeah, get on. 2 doors open, I'm in and out. Ain't no minute high, ain't no minute high. I wanna. LV baby, swag on me. Without cash, that intimacy. Shawty shake, ask, get cash for free. Shawty shake, ask, get the cash for free. We always feeling right, hey. It's one of those nights. Everything feeling right. You can feel it right, girl. You can feel it right. You can feel it right. The spark from the lights, girl. Flash in her eyes. She's a single friend of mine. Yeah, make the girls high. She keeps singing him and I, as if we're Gemini, like we're till the night. I wanna. It's alright, I'll be okay. They like 50K today. You can go or you can stay. Tell me you're ready to leave the place. Hundreds in my bag, don't need no more. Up all night till I break the code. See this when I lean to the door. Can't find a Sprite, then I'm dropping in the moed. Twin bitches hopping off a jet ski. Yeah!
Hold up.
Every day when I'm spreading no doubt communication, they say that they wanted a piece of the bread. It's too late, cause the breads that I made isn't for the tape, but instead I just give it to people that made all the thoughts that I had in my mind when I started the day, walking into the night, and they give me my morals that take all this knowledge inside of my mind to a different direction. And to me, it'll count as a blessing. To you, it'll count as a lesson. Picture inside of your mind of a young little kid with a dream and no stressing.
But it's just hard.
Every day when I'm spreading no doubt communication, they say that they wanted a piece of the bread. It's too late, cause the breads that I made isn't for the tape, but instead I just give it to people that made all the thoughts that I had in my mind when I started the day, walking into the night, and they give me my morals that take all this knowledge inside of my mind to a different direction. And to me, it'll count as a blessing. To you, it'll count as a lesson. Picture inside of your mind of a young little kid with a dream and no stressing.
Certified banger. Certified banger. That's going somewhere.
Hello, everyone.
Oh, what the? My fault. I need to delete these. Wait, not the stew. I don't even be in the stew.
Yeah, hey, yeah, hey. I'm keeping it sis though. Attitude while I feet though. Put the pedal to the metal while I swim cold. And the sound that I bless while I fly by the past. Got me feeling in sport mode. Got rid of the past, now in the future. And people move on while I'm stuck in the oh yeah. Yeah, hey. But this ain't the end for flowers to bloom. They gotta shit us to start. It's something that was made brand new. You knew from the start. Couldn't be taken apart from the moments we had in the past. And when you start reminiscing on reasons we had to not be together and give up on feelings, and made it all look so sad. Yeah. Yeah, hey, yeah, hey. Still chasing these dreams though. Pour six for the field show. Different moves every day, but I always feel so low.
That's a certified banger. I really sold on the quiz. No, this hard. It's hard.
Yeah, hey, yeah, hey. I'm keeping it sis though. Attitude while I feet though. Put the pedal to the metal while I swim cold. And the sound that I bless while I fly by the past. Got me feeling in sport mode. Got rid of the past, now in the future. And people move on while I'm stuck in the oh yeah. Yeah, hey. But this ain't the end for flowers to bloom. They gotta shit us to start. It's something that was made brand new. You knew from the start. Couldn't be taken apart from the moments we had in the past. And we start reminiscing on reasons we had to numb it together and give up on feelings and made it all look so sad. Yeah. Yeah, hey, yeah, hey. Still chasing these dreams though. Pour six for the field show. Different moves every day, but I always feel so low.
I could have waited so long. I could. Nah, that was something for sure. Alright, know what it's on. Yo, I low key trying to go study though. No. Oh, there's like more videos. You got me messed up, dude. Mm-hmm. Wait, we didn't even finish it. Oh, still haven't finished it. My fault, twin. My fault. That's a zero. If y'all wondering what the little dash is, it's a zero. I forgot to do a quiz the first week, cause I saw it, and but he said he gonna drop one. Yeah, the exam, like that's the only thing that's graded. So I got a zero. Yeah, the grades not looking too good. I got a 90 on this exam. Still an A, but I don't know. I could have got 100. Should have got 100. Dang, boy. Yeah. What I really want to do. Uh, yeah, so okay. Yeah, I have electrical systems exam, programming concepts exam, and it's a solid exam before spring break, which is kind of evil, but they're in 2 weeks. The 11th, 13th, and I have an exam this Friday, what I should go study for. I will go study for. Yeah. So, I was gonna put y'all on real quick. This one song. Oh wait, Wet my hair. Yeah, okay, check this out. This dude, he got like no followers, but golly, can he make some music?
I'ma keep my distance, tryna find my head, I know that I'm in it. Can't fear how to stand on business. Shit ain't shit fair, niggas came up missing, but I still ain't tripping. Should I put in the time to get it? Should I put in the time to spend it? Fuck is you talking about, baby? She tryna talk about bundles and Sadies. I'm tryna talk about nothing, shit pay me. Yeah, I'm tryna talk about nothing, just pay me. I'm tryna make sure my people them good shit. I'm tryna talk like I'm comfortable, baby. I got it off, ain't had nobody save me. It's double the cost for the FIFA, you hate me. The fuck is you talking about? Shit, I came from the pit, so I can't miss. Had to make me a flip, had to change shit. I grew half the niggas I came with. I done dropped out of school, so I can't quit. Put that shit on my mama. All them days she was crying, just trying to make a way. I ain't here for the drama. I can't stress about a hoe I ain't found when I need a ain't no question. I'ma keep my distance, tryna find my head, I know that I'm in it. Can't fear how to stand on business. Shit ain't shit fair, niggas came up missing, but I still ain't tripping. Should I put in the time to get it? Should I put in the time to spend it? Like I'm tryna be the first one to touch a meal in the city when niggas don't get a meal. I know niggas in school tryna get a feel. I know niggas with tools tryna make a deal. I know niggas with shit hitting deep, still tryna battle. If I'm lost on a key, I'ma get it no matter the cost of the feat. Shit, I been underneath screaming R.I.P.E. Yeah, it ain't no question. I'ma keep my distance, tryna find my head, I know that I'm in it. Can't fear how to stand on business. Shit ain't shit fair, niggas came up missing, but I still ain't tripping. Should I put in the time to get it? Should I put in the time to spend it? Yeah, it ain't no question. I'ma keep my distance, tryna find my head, I know that I'm in it. Can't fear how to stand on business. Shit ain't shit fair, niggas came up missing, but I still ain't tripping. Should I put in the
The Marcus made it, you know it's a hit.
I be shining brighter than a light, man. Checking out the shawty with the Nikes. Ass fat, but the booty don't excite me. Tell me all about your goals and your life dreams. I don't wanna die here. Rather be alive and be a villain. That's the type of shit that I've been feeling. Only took a week to deal with the healing. After that, I wanna turn up the city on some brown shit. Two bitches want me up and I'm a pop shit. I've been bad, bad, bad like the posh. Watch your back, you could never be too cautious. After that, I wanna turn up the city on some brown shit. Two bitches want me up and I'm a pop shit. I've been bad, bad, bad like the posh. Watch your back, you could never be too cautious.
Yeah, bitch, I need commas, they know I'm not finished. I need me a plug at a call on my desk. Like hit the chain back and forth, this shit a test. You ain't get explicit, you weighing the tennis. I got like forks and scamming and forks. I gave them a 10 while they forks to 40. They saw me popping off, I put a drop it off. Bitches ain't care how these bitches ignore me. I got like 40 ball off for that 10, but you know that I ain't gon' give it a shorty. I just put 70 on a new Benz. These bitches ain't telling me I got a hold.
Why the fuck would I hold some shit for you? Can't even respect. I went out of my way, little bitch, just to text you. But still, you moved on to the next one. Goddamn, I hope that you do you wrong, so I'll correct you. Like, ha, feeling stupid now. Got a chip on my
That was that one. There's another one. That's fine.
Yes. You know, I had to go turn off my air freshener, man. Shit was just too loud. But it was blowing Joshua Tree in the air, and it smells mad good in here. Yes, I might just go out to France and do my little dance. Don't need no advance, little baby, I'm good over here. Show me some love without saying you love me. You turn around and put my face in your rear. I don't need model, but baby, you model. You tell me that I look as good as your peers. Like Vincent Van Gogh, I'm painting my soul. You telling me no, I'm a Ooh, cut off your plans. I'm not a jabroni, I'm not your little homie, I'm not one of them. Popping the collar, I dollar the holler like fuck out of Prada. I'm rocking a brim. I'm wearing this, ooh, that's fitting me well. Dressing real good and I like how I smell. Not joking around, I am not no Chappelle. I'm cropping through lanes, man, I feel like Geppetto. Might just go turn up a whole nother level, a whole nother bezel. I really am him. Fitted as fuck, I don't give a fuck. I'm walking New York without wearing some Timbs. Like, baby, listen, these are not stock, they ready to rock. Low profile rims, I know the maneuver. I pull up on scooters with baggy ass clothes. Now I might just go out to France and do my little dance. Don't need no advance, little baby, I'm good over here. Show me some love without saying you love me. You turn around and put my face in your rear. I don't need model, but baby, you model. You tell me that I look as good as your peers. Like Vincent Van Gogh, I'm painting my soul. You telling me no, I'm a... Cut off your fucking ears, bitch. You talking about the music ain't that good, this and that. Bitch, you don't think this is good. You don't even deserve ears anyways. Stupid bitch.
If I love you in the right way, would you change for me? Do the same for me. I hope you know you all that I need. Yeah. Lady, I still can't fall asleep. 'Cause I'm thinking about you. Yeah, 'cause I'm thinking about you. 'Cause I'm thinking about you. Yeah, 'cause I'm thinking about you. Would you change for me? Yeah, do the same for me. I hope you know you all that I need. Yeah. Lady, I still can't fall asleep. 10 bands, 50 bands, wedding bands. Yeah, she tryna break us up cause she can't get a man. Look at them talking on me, oh there go another fan. I done fell asleep, woke up to another 100 grand. Yeah. Don't fuck with me, go get another man. Gotta go and take a break and make some other plans. You was my right hand, put something in my other hand. I live a lifestyle that's hard for you to understand. If I love you in the right way, would you change?
Right way. Change. Straight dynamics for 8 hours. And I hit the gym at like it's a good time. Or maybe I can do some coding. Sound like a plan. Sound like a plan. I love it. Change for me. Same. Frank. How did I get 50 something on that quiz?